So today we're going to start transition elements. It's actually become a very popular chapter in the exams because it's the only thing left from inorganic chemistry, really, if you think about it, in the A2. Now, and the first thing we'll start off with is the first thing you need to differentiate is the idea that what's the difference between 3D elements and transition elements, and they are not the same. D block elements and transition elements are not the same. Now D block में क्या आता है? D block में आप एक calcium के बाद आते हैं. In your notes, it's the first slide. You got scandium, you got titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. The problem is that scandium and zinc are 3D, are D block elements, but they are not transition elements. And you might wonder, well, ऐसा क्यों है? Because the properties that we associate with transition elements are not found in scandium and zinc. And those physical properties are that they exhibit color in their solutions. Now, the reason why they can't exist color in their solutions is because of a particular reason, and we'll talk about that as a definition of transition elements. But the property that we know about transition elements is that all of them in their aqueous form have to have color. And because they have color, it means they have a few properties. Few properties like they will make complex ions, is that they will, what we say, bond with ligands to make those complex ions. Electrons will transition. Then the name transition is for electron transitioning from a lower energy state to a high energy state. So the term transition can only happen when there is color. So having color is an indication of electron transitioning, and that can only happen in one condition only, which is that these guys have to make ions with partially filled d orbitals. So let me repeat that. This is found in the second slide of your notes. Is that a transition element is a transition element when it forms a complex ion, forms at least one ion, not all, but at least one ion that has a partially filled d orbital. Now, what does it mean by partially filled d orbital? D sublevel or D subshell. What that means is that there's a 3D, for example, in the third shell. The 3D में 1 से लेके 9 तक होने चाहिए. Meaning the ion should have 3D 1, 2, 3, 4, 5, 6, 7, 8 or 9. And why therefore is scandium not an element? In your books in slide 2, you will realize that scandium Sc only makes one ion. Now scandium has a proton number of 21, which means its configuration is 1s2, 2s2, 2p6. This is in your notes on slide number 2. 3s2, 3p6, 3d1, 4s2. Scandium's configuration in the outermost shell is 3d1, 4s2. This is in your slide 2, if you notice at the bottom of the slide. And scandium only makes one ion. It doesn't even make multiple ions. It only makes a 3+ ion. When it makes a 3+ ion, it loses the outermost shell, which are the 4s2 and then the 3d1. So the configuration for the 3+ ion ends in 3p6. What that means is 3d is now empty. So scandium by definition had a completely empty 3D subshell, the ion 3+, which means it was not partially filled. And by definition, if it's not partially filled, we cannot call it a transition element. Now, बाकी सब में होता है सवाय zinc के. Zinc में भी, now zinc's configuration is argons plus 3d10 4s2. But zinc also only makes one ion, Zn 2+. And when that happens, the outermost two are lost, which are the 4s2. Again, this is also in the same slide number 2 at the bottom of the page. Look at that slide. It says zinc has a 2+ charge and the configuration is 3d10. Now 3d10 means that 3d is completely full. This is completely full. Now when it's completely full or completely empty, it negates electrons transitioning within the 3d. Because there's either no space to transition or they're completely empty. And this, when we do colors next class, you will understand why this matters. Actually, not this class, next class. You'll understand why this matters. Because unless unless they are partially filled, you're not going to have color. And if you can't have color, it won't have the one property that we name them by name. The name is transition elements because we want electrons to transition, and unless they don't transition, they don't have color. Now, how do they have color? I have not taught you that. But for now, you need to know it depends on the fact that their ions must have, because the color is from ions, the ions must have some empty space, not completely empty, but some electrons and some empty space in 3D. So the 3D cannot be full, ion cannot be empty. So that's why zinc and scandium are not transition elements, but they are D block elements. Now, and so when we discuss today physical properties like size and ionization energies, we will consider the whole D block. But when we start doing chemical properties like colors, like reaction, like variable oxidation state, we will not be considering scandium and zinc, because then we will only talk about transition elements. But for physical properties, we will talk about 3D. अच्छा, हम 3D की बात क्यों कर रहे हैं? Because we are not going to study 4D and 5D. Because 3D की properties are the same for 4D and 5D, obviously except for exact colors, but we don't care about exact colors. We care about the general idea. And so this whole chapter, let me give you a summary of the whole chapter, will involve a bit of physical property, ionization energies, and atomic radius and ionic radius. Then we go on to the fact that they make complex ions, which is the reason why they even have color. Then when we make complex ions, then we'll talk about shapes of complex ions. Complex ions will have shapes like tetrahedral, octahedral and stuff. They will also have optical and cis-trans isomerism. Then we talk about ions that make complex ions with zinc. You already seen complex ions in AS level with the silver and group 17 reactions. When you add silver nitrate with excess ammonia, silver chloride dissolves to make that complex ion. You've seen one of those in AS. Now, so we'll do that. Then we will talk about, we talked about cis-trans and all that. Then we talk about some ions ki specific colors like copper. Because you know from AS, copper in pani mein, and NaOH mein, and ammonia mein has different color. We'll talk about those. Then we'll explain to you how the hell does anything even show color. And we'll therefore, for that, we will need to talk about the 3D orbitals also. There are 5 of them. So we'll study their shapes, their planes, their orbitals. Then we'll study their transitioning, which is why they'll have color. And then we'll also do their isomerism and complex ion and all of that. Then at the end of it, complex ions may, there'll also be equilibrium reactions. So there'll be a particular equilibria we'll study also for this. So there are about 4 major classes of theory for this. Okay? Now, what we're going to talk about second is the size, the atomic radius of D block elements. Now, like I said earlier, that we will discuss the whole D block, not just transition for this, because it applies to all of them. Scandium, like zinc. Now, you need to first remember generally how does atomic radius vary across a period. And for that, ये AS की theory थी जब हम period 3 के बारे में करते थे. Period 3 में what happens across the period to atomic radius? It decreases in size. Across a period, atomic radius drastically decreases. So much so that the sketch of the graph looks something like this. It's like downward sloping from sodium all the way to chlorine. Obviously, we don't draw argon because argon's flaw, measurement has a flaw. But this is a general trend of ionic radius across a period. Now, when we come to, and the reason why this happens, and you have to remember that, is that when you go across a period, you need to remember the terms. Nuclear charge is increasing. But because the electrons are going in the outermost shell, the shielding remains the same. Now, the shielding effect remains the same, and only the nuclear charge increasing, the outermost electrons are attracted more and the atom gets smaller. But problem with transition elements is that, when you go from scandium all the way to, for example, zinc, when the atomic number goes from 21 to 30, the electrons in the outermost shell are not the ones increasing. Because scandium is 3d1 4s2 and zinc is 3d10 4s2. So electrons सिर्फ कहाँ बढ़ रहे हैं? 3Ds में. 3d1 से लेके 3d10 तक जा रहे हैं. When 3D is the third shell, not the fourth shell. So what's happening is the inner shell electrons are being increased as you go from here to here. when inner shell electrons are being increased, the shielding effect will also increase. So transition metals may, across this list, it's not only that nuclear charge is increasing, but also shielding is also increasing. And the net effect is almost balanced out, which is why this particular graph exists. That if you notice the solid line, that is a period 3 trend for size. But look at the dotted line, especially after the first two, they're almost horizontal. And we won't worry about the little hiccups, but they're almost horizontal. And why does the atomic radius for transition elements remain almost consistent? Because even though there is an increase in nuclear charge, it is balanced by, or it's almost balanced by counterbalanced by the increase in shielding effect. And the questions will ask you that, and you have to write that. Okay, describe and explain the trend in atomic radius for transition elements, or D block elements for that matter. And you will say that even though the nuclear charge is increasing, but the electrons are being added to not the outermost shell, but the inner shell, which means that the shielding effect will also increase, and that increase almost counterbalances the increase in nuclear charge, which is why the size looks to be almost the same, almost constant. While in normal period 3 mein, the size is going to decrease. So you'll have to remember that for this. So let me actually even repeat this, and then I'll show you the graph also, just to match it. And so somebody said they didn't get this, so I'm going to say it again. The same factors that affect atomic radius also affect first ionization energy. In a normal period 3, period 2, period 4, across a period, nuclear charge is going to increase and the shielding remains the same, which means the ionization energy increases like this yellow line graph. But in transition elements, the nuclear charge increases across a period, and also the shielding effect also increases. And the reason why that increases is because the additional electrons are not being added to the outer shell, they're being added to the inner shell. So the number of inner shell's electrons increase. And it's those inner shell electrons that are causing shielding. So जब वो बढ़ेंगे, तो shielding बढ़ेगी. And when shielding increases, it almost counterbalances the increase in nuclear charge. Which almost cancels it out, but थोड़ा सा बच जाता है. That's why it doesn't remain constant, but it only slightly increases. And I can show you the actual graph, Nietzsche, 1 second. The graph that I'm talking about is, so your slides 9 have this graph. This is a normal period 3 graph. You can see the ionization energies are increasing, but for transition elements, they're remaining almost constant. Okay? And that is, I explained to you why that is the case. All right? Now we're going to talk about the shape of the 5 d orbitals. That's the next thing on our agenda. This is skipping a few slides because I would like you to just go through them yourself. Those are the same things you've done in AS, how to write the configuration for transition elements, the 3D filling after the 4s. That stuff we've done before. So you can go through that from there. What I want to focus on is d orbital stuff, which is your job is to be able to draw the d orbitals first, which is that there are 5 of them. And they actually look like, if you want to draw them out, 4 of them have the same shape. And that shape is like 2 p orbitals, like this. 4 circles in a way, or just like 4 of them between the quadrants. Now, don't worry if they're between or on, but this is the general shape of 4 of them. The 5th one looks like a p orbital with a donut through it. So there are 4 that have these 4 lobes, and the 5th one is like a p orbital with a donut through it. But they're not their planes matter. Like we'll need to know कि कहाँ का, because in p orbitals you've got the px on the x-axis, you got the py on the y-axis, and you got the pz on the z-axis. Now d में मसला ये है कि you'll find some of them जिनके ये lobes हैं, look at the bottom 2, these lobes are on the axis. जहाँ 4 थे, so there are 2 of them on the y and 2 of them on the x. And this one is called x square minus y square. And the weird shape one is called z square, the other one that's different from all shapes. Now these 2 are called the 2 orbital group. ये आप लिख लें, add कर लें, 2 orbital group. And the reason why they call the two orbital group is because there are two of them. They are basically इसमें क्या है? The orbitals are lying along axes. And you'll notice the difference in a minute why this matters. It will matter quite a bit, but right now the difference is also going to become obvious. Now, and I'll draw them out for you also, the difference. But these two are the two orbital group, and the names are x square minus y square and z square. It's very small print here, but you know what it says in your notes. This left one is d x square minus y square, and the right one is d z square. So these are your two orbitals groups. The two orbitals the x square minus y square means the four lobes on the x and the y axis. Z square means the lobes are on the z square axis, and around it is your donut. The above three are called, this one is dyz, this one is dxz, and the last one is dx and y. And the difference is that, the difference really is highlighted if I can focus on how is xy different from x square minus y square. X square minus y square में ये चारों lobes हैं ना, they were on the axis. And xy में the lobes are between the axes. This is called the three orbital group. And they are lying along between the axes. This is along the axes, these are between axes. Okay? Now, it's very easy to see it like this. That let me zoom out for a second. So when I said dx square minus y square, and if my planes are x and y planes here है, तो मेरे ये है dx square minus y square. Although they are on the axes like this. This is how you draw dx square minus y square on your exams, because they can ask you that. This is the x-axis, this is the y-axis. But dxy made on the same axes, oh come on. Now the next one I'm drawing, this one is called dxy. And how is this different is, imagine you have this thing rotated clockwise by 45 degrees. So all these four lobes are now going to be found between the axes like this. ये वही चार lobes are now between the axes, where this is x and this is y. So the difference, the two types are, in one type the lobes are on the axis, that's x square minus y square, and between the axes become dxy. And if this is xy, यही चीज z में भी xz में भी हो जाएगी और yz में भी होगी. But that's the difference between the two types. These are the types, the two orbital groups are lying along the axes. This is one of them, x square minus y square. And xy or xz or yz are the three orbital group. They are lying between the axes, where the lobes are in the quadrants, not on the axes. And this sets them apart, because if we don't, we need to divide them into two groups, because eventually when we do complex science and when we do colors, the differences will come because of these two types of orbitals. कि axis पे कौन सी हैं और between the axis पे कौन सी हैं. So, but before we do that, this is what you need to know first. To be able to draw the 5D orbitals, to know that there are two types of them. The types are two, not by the shape, but by their layout. There is one type that exists between the axes, and there is one type that exists along the axis. Between the axis, you can make x, y, x, z, or y, z. Along the axis, you got x square minus y square, and you also got z square. जिस तरह बनी हुई है यहाँ, मैं कभी एग्जाम में बनाऊंगा नहीं, बिकॉज वो चॉइस नहीं है बनाने को. अगर आपको बनाना पड़ा जी एक्स स्क्वायर जी स्क्वायर, तो आप बोलेंगे इस एक्सिस को जी ले लें. You can decide which axis is what. And then you'll make like this, z square mein ye ho jayega. And then you can say, well, a donut aage piche like this. Before we continue with the next thing, which is complex ions, let's recap what we've done so far. The fact that what defines a transition element is that it has a partially filled d orbital. It forms at least one ion with a partially filled d orbital. And just to even highlight that, repeat that once more, I'll give you an example from iron. Now, iron is Fe. Iron can make Fe2 plus and even Fe3 plus. And iron's configuration is 1s2, 2s2, 2p, 6, 3s2, 3p, 3p6, 4s2 mein, 3d mein bhi 6 hai. So when it becomes Fe2 plus, it only loses the 4s. And when it becomes Fe3 plus, it will lose the 4s ka 2 and the 3d ka 1. And baki sab same honge yahan. You know? So iron clearly has at least one ion with a partially filled d orbital. That's why iron is a good transition metal. Copper is another example, by the way. Now, copper is the exception, if you remember. The exception was that argon, argon is 3p6, and copper was 3d10, 4s1, instead of 3d9, 4s2. You must remember that from AS level. Then when copper becomes 1 plus, what will the configuration be? Argon, 3d10. And you might say, well, that is not a partially filled d orbital. But we don't have to have all of them partially filled. We can have at least one, because the copper 2 plus is that one. 3d9. So that's why these guys are transition metals. That's the first thing we did. Then we discussed that atomic radius and ionization energies ka farak isme aata hai, because for all transition metals or even d block elements, when you go across a period, nuclear charge is not the only thing that is increasing. Because the electrons are going in inner shells 3D, they're also increasing shielding. And increase in shielding almost counterbalances the increase in nuclear charge, which is why the size only decreases by a very small amount and ionization energy only increases by a very small amount. We can say they almost, for all practical purposes, they remain constant. And that was the physical properties. Then we studied the shape of the d orbitals. There are 5 of the d orbitals. The names are xy, xz, yz. Those are the ones that lie between the axes, and then there are x square minus y square and z square. These are the ones that lie on the axes, along the axes and between the axes. इनका बाद में मसला आएगा फर्क वरक, अभी पांचों सेम है. ठीक है? Next up, complex ions. Transition elements have a tendency to make complex ions, and the reason for that is these guys are small and have very high charge, like 2 plus, 3 plus, 4 plus. Especially 2 plus and 3 plus. What it does is they attract electrons. And an example is, जब आप पानी में घोलते हो ना कॉपर को, चलो कॉपर anhydrous होता है सफेद. But the moment you add copper to, let's say you have copper sulfate, right? You have copper. What the hell is happening here? Copper sulfate. Now, if it's anhydrous, you might remember copper sulfate anhydrous as what color? White. But you mix it with water, it becomes blue. The reason why it becomes blue is that electrons are transitioning. They can transition because they need to transition. And that comes from the fact that they can form complex ions. So what's happening is the blue color of what copper is because of the complex ion CuH2O 6 times 2 plus. And what is really happening is that copper 2 plus से 6 पानी के molecule bond बना रहे हैं. Like one like this, one, and the bonds are along the lines of the understanding of like dative bonds. Because dative bonds के लिए what do you need? You need lone pairs. So it's not as strong as a normal covalent dative bond, but it's along the same lines. And ये आपकी notes में बना हुआ है, but I'm trying to make a very cute little diagram here. I think I started going on that, and I think it's just beautiful, turning out very nicely. And there's one ऊपर, one नीचे, one left, one right, and one G आगे और one G पीछे. And that, in fact, also makes. So copper is surrounded by 6 water molecules. Now the reason I'm drawing it is because eventually you also have to draw this for the exam. And the whole thing gets a 2+ charge because copper has a 2+ charge. But why does it even happen? Why did water molecules bond with copper? Because copper has a high charge density, 2+. It tends to happen with transition because they're smaller and they have 2+, 3+ charge. Group 1s have a 1+ charge, not so high density, charge density. These guys have more tendency to attract electrons. Electrons are negative particles. So this guy attracts 6 electrons from 6 different sides. And that's how 6 waters have been able to be attracted to copper. These are dative bonds, kind of bonds. And here, water is called a ligand. Because the ligand was used to make complex ions with transition element central cations. So, your job is to know that complex ions can form, and complex ions forms by making dative bonds with other molecules or even anions, by the way, because those guys have lone pairs. And the whole thing is called a complex ion, and those molecules or ions having a lone pair are called ligands. And this whole thing is called a complex ion. Yeah. Now, the bonds are what kind of bonds are these? These are dative bonds. Dative bonds. It's a complex ion formation, which is why a lot of these ions make bonds in the human body also. Hemoglobin and stuff like that, for those who take bio. Right? Now, what are ligands? Ligands are these small molecules or anions that have a lone pair. And the reason why they're called ligands is because they can make dative bonds to make complex ions. Okay? Now, every time you mix any of these any of these transition metal ions into water, they will make this complex ion. You can even realize what shape this is. What shape is this around the copper? Octahedral. So, even if you did this with iron 2+ ion in pani makes what? Fe, H2O, 6 times, and square brackets with the whole thing into a 2+ charge. That is, that Fe has made 6 bonds. And now I'll make the octahedral the other way, in the way that's easier to draw probably for the exam. In the plane like this, and showing all the bonds are how much? 90-90. And you got the OH2O this way, OH2O this way, because it's bonding with O, the O part of the water. And this is them making 6 bonds, and you will have to be able to draw the complex ion. You'll have to be able to recognize the shape. This shape, though ugly drawn, is octahedral. All the bonds are going to be 90-90-90. ये ऊपर नीचे हैं ये, and these 4 are on the horizontal plane. If I had drawn it very nicely, though I didn't too much, these 4 bonds are like on a horizontal plane. And उसके ऊपर और नीचे भी पानी है. 6. You can eat, it's actually the full name is Hexaaqua, iron 2. We won't worry about names in A levels, but each complex ion has a name. जितने ligands लगे हैं उस पे, और ligand का नाम, और iron और metal का नाम, और उसका oxidation state. Hexaaqua iron 2. Obviously, you can get Hexaaqua, you can also get other forms. You can get Fe, H2O 6 times, 3+. Cobalt will also do that. Cobalt 2+ will have cobalt H2O 2+. Chromium, the dark green solution is chromium H2O 6 times, 3+. The charge is the same as the cation because molecules are neutral, but they don't have to be molecules. They're also anions. And this is, a good example is drawn in on slide number 23 for you guys. There are all the types of complex ions you can have. ये octahedral हो गया. I'll show you tetrahedral. Very popular tetrahedral complex ion is CuCl4 2-. That is Cu, but now instead of 6 bonds, there are 4 with chloride ions. But these are dative bonds. And since copper is 2+, and each of these chlorides is 1-, there are 4 minus ions and 2 plus. Net charge क्या हो गया? 2 minus. Tetrahedral complex. There are some that are square planar. Platinum is a good example, and you'll have to learn it. Platinum with 4 chlorines. Now platinum 2 plus with 4 chloride ions is PtCl4 2 minus. अच्छा, इसमें it's not tetrahedral, it is square planar. Square planar is like making the square of the octahedral without the 2 bonds above and below. All bonds in this case will be 90. Cl, 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 Cl. The whole thing having a 2 minus charge. You also know linear. AgNH3 twice in AS level was linear. It had 2 bonds with 2 ammonias. Linear. Okay? So, slide number 23 has the 4 shapes. Those shapes come in handy for tetrahedral. Here are the 4 diagrams drawn in your notes. The octahedral, the tetrahedral, the square planar and the linear. Guys, what you will have to learn is that every time you have 6 water molecules forming, you will make an octahedral complex. You'll have to know that certain, specifically CuCl4 2 minus, you have to learn that is tetrahedral. And you have to know from AS level that ammonia with silver is a linear ligand, linear complex ion. And anything with 6 water molecules, any metal with 6 water molecules will always be octahedral. Whatever charge 2 plus, 3 plus, 4 plus. Square planars will be told to you. You'll be specifically told, yeah, ye square planar hai, then you can, don't worry about it to know. You'll be told in the question, yeah, ye square planar hai. Okay? One thing more that you should know is something called coordination number. Now, coordination number is the number of bonds being made. So now how many bonds are here? 6. The coordination number here is 6. Here the coordination number is 4. Here is also 4. And this is 2. So exam mein you'll have to be able to make the complex ions, draw the shapes. Now these are not, यहाँ clearly 2 ligands थे, 3 है, ammonia भी है ligand, पानी भी है और Cl minus भी है. These are 3 more popular ligands, but you have others also. Anytime you have a lone pair and a small molecule, it has a tendency of making bonds with the metal cation. It will be a ligand. Cn minus ions, where the lone pairs of nitrogen and carbon, they also act as good ligands, what the carbon does. The carbon is one that makes a dative bond. So cyanide ions are also good ligands. Okay? And all of these, by the way, come in the category of monodentate ligands. Because if you think of the dentate comes from the fact that they make one bond. So all of these molecules are making a single bond each. And the reason why this matters is because tomorrow we will be doing molecules that are called bidentate, where one molecule can make 2 of these dative bonds. Not the fact that it has 2 lone pairs, but that it has 2 ends of the molecule that will have lone pairs, and they will. So it'll end up being something like this. So that I'm going to leave you with that thought. Is that when a bidentate ligands, for example, form, and you got octahedral complexes like this, like 4 bonds you hain, aage piche. So what you realize is that bidentates, now instead of having 6 individuals, there will be 3 making 2 bonds each. Like 2 with this like this, 2 like this, and 2 bonds like this. Something will come and bond here and here, something will come and bond here and here. So it will be octahedral, there will be 6 bonds, but there will only be 3 molecules. The yellow ones can be considered the molecules. Each molecule making how many bonds with the central atom? 2. And it look like teeth coming in claws, hence the term dentate. So bidentate versus monodentate. So tomorrow we'll continue with this.